The first topic of the second unit of the course is the principle of mathematical induction, and this regards statements about positive integers that we're going to be proving. We'll start with an example. Here's a statement. Let's see, our statement would be that the number n squared plus n plus 41 is prime, and that's a statement about n, which may be true or false. We're going to try the first several positive integers for n to see whether the statement's true or false. So when we take n equal to 1, we actually get 1 plus 1 plus 41 is equal to 43. When n is 2, we get p of 2 would be 2 squared plus 2 plus 41 is prime. That's the full statement that I've written out there. Well, that'd be 47 is prime, and in fact that's true. That's true. Try that again. That's true. As is this first one. This is prime. Yeah? And we could keep doing this. You know, we could keep doing it with n is equal to 3. And when n is equal to 3, we get 53. Again, prime. And so forth and so on. In fact, we could go all the way to n is equal to 40, and we'd get 1681, which is also prime. So, you know, you might think, well, is it always prime? But we've gone as far as we can without hitting a composite, because when we look at n is equal to 41, we get 41 squared plus 41 plus 41, which clearly has 41 as a factor. And in fact, this is, you can quickly calculate it. This is 41 times 43. Just factor out one of the 41s, and this is not prime. So, but this is a statement about a positive integer, and just to show you that you can certainly have them where they're sometimes true and sometimes false. We're going to use a symbol p of n to refer to a statement about n. And we'll be thinking of n as a positive integer, but in the statement itself, it doesn't necessarily reference that. So a statement here is a sentence that asserts something is true or false. In the example above, Pn is the statement that n squared plus n plus 41 is prime. So we know from our example that this is sometimes true. And in fact, it's true for all integers between 1 and 40, but it's false at 41. It's false for any multiple of 41, and there's many other places where it is not prime. 44, 49, 56 being some examples of many. We're interested more in cases where we can prove something is true for all positive integers. And the principle of mathematical induction is a nice tool for that. It's a great tool for proving something like that. So here's a statement of it. Suppose that p of n, like so, this is not a function, it's simply a symbol to represent a statement about the positive integer n. Now, if we have the following, then we'll be able to conclude it's true for all positive integers n. So here's what the principle contains. If p of 1 is true, namely the statement is true when n is 1, and whenever p of k is true for a positive integer k, then p of k plus 1 is true. That is, let me rephrase that. If in the long infinite list of positive integers, we look down and there's a positive integer k, and the statement is true about that k, then point 2 here says it's also true about k plus 1. If it's true for 1, and it's always true whenever we have a positive integer, it's always true for the next one, then that means that we can take one step at a time of one integer of length 1 to go from one integer to the next. And every time we do that, if we are at a place where it's true, then it will be true in the next step. So starting at 1, that would imply that 2, it's true at 2. It is also true at 3. It is true at 4. Each time, taking a step of length 1, it retains the truth, and so it must be true for all positive integers n. We don't miss any of them in taking a step of size 1 each time and retaining the truth thereof. This says that you retain the truth when you go from 1 where it's true to the next 1, to the next larger integer. So we use that in proof technique in the following way. Proving that a statement Pn is true for all positive integers can be done the following. First of all, we identify the statement P of n, and I'll always include that in the proofs. Then we will prove that P of n is true when n is equal to 1. That's the same as saying P of 1 is true. By the way, this is called the basis step. And second, we'll prove that if P of k is true for an integer k, then it must be true for k plus 1, the next integer in line. And that is enough to prove that it's true for all positive integers n. So our first proof of this will be to look at the sum of the first n odd positive integers, where n will be any positive integer. So the first one positive integer is 1. And so if we just take it, it is equal to 1. If we take the first 2, so this is n equal to 2 odd positive integers, and add them, then we get 4. So here we're just trying to figure out how this is going to work out, make a conjecture. Now if we take the first 3, n equal to 3 odd positive integers in order, the very first 3 of them, and add them, then we get 9. And if we take the first 4 of them, n equals 4 now, and we'll take the first 4 of them, we'll get 16. And what it looks like is we're getting the squares of however many integers we're looking at. So this appears to be n squared, where n is the number of odd positive integers starting at 1, 1, 3, etc., up to whatever the nth one is. So the thing here that we want to figure it out is, what is the nth odd positive integer? 2n minus 1 will give us that nth odd integer. And so right here we have a conjecture. Our conjecture is that 1 plus 3 plus dot 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 plus 2n minus 1 squared, or is equal to n squared, where this is the sum of the first n, that's how many there are, odd positive integers, and it turns out to be n squared, which is exactly the square of how many odd positive integers we have over there. By the way, just one comment about this 2n minus 1. This one is 2 times 1 minus 1. 2 minus 1 does indeed give us 1, and that number there is the counter. That's 2 times 2 minus 1. That indeed gives us 3, and so that's the second one, and that's the nth odd positive integer. So in the next video we'll actually go through and construct the proof of that, but this is the way one can come up with formulas, at least a conjecture. We'll stop right there.